Okay. Hello, everybody. Thanks for coming to my talk. My name is Sitnik, and today I will speak about state of the .NET performance. Who am I? I'm one of the core contributors to Benchmark.net. It's the most popular library for benchmarking .NET code. I also maintain the awesome .NET performance list, and I contribute to Core CLR and CoreFX Lab. I work for Powell. It's a Norwegian company, so it's very special for me to speak here today in Oslo because we make things in Oslo work. My main goal is to share the knowledge with you and to speak about all of the new things. I'm not going to speak about improvements. I would like to show you the new shiny things that you can use and make your applications faster. But one very important update. On Monday, I have realized that David Fowler, who has implemented pipelines, was going to speak about pipelines. Have you been to his talk yesterday? The audience was full. So instead of pipelines, I have decided to take this time and speak about C# 7.2, which is super cool in terms of performance. So let's get it started. You might be surprised that I start with value tuple, because it's just a tuple. It's very flexible, and we no longer need to create a dedicated type when we want to return more than one thing from a method. But the key is that it's a value type. And there is a huge difference between value and reference types. And it's a key to understand it to have a good performance. And today I will speak about few value types. So this is why now I'm going to briefly describe the differences. And to make it simpler, I will talk about value tuple and tuple of two integer fields. So, first of all, we have an extra overhead. Each instance of a reference type contains two extra fields: pointer to the method table and object header. So, for example, when you take a lock on your object, CLR is writing information about this to the object header. When you invoke virtual method, it jumps to method table, and then it jumps to the implementation of your method. Also, reflection is using this. But the point here is that we have extra overhead in terms of memory. So for two simple integer fields, we have tripled the amount of necessary memory for 64-bit architecture, which is recently the most common one. When it comes to value types, we don't have any extra overhead. What you see is what you get. But they are more limited. You cannot take lock on them. They cannot have finalizers, and you cannot derive from them. So it comes for a price. But to understand how it affects the performance, we need to understand how CPU works. So when you want to read something from memory, CPU is first of all looking for the value in the cache, in the first level of cache. If data is not out there, it goes to the second level. If not there, it goes to main memory. But this has different prices. So, accessing first level, half of a nanosecond. Second level, 14 times slower. Going to main memory is 200 times slower. And CPU knows about two principles of data locality. First one, temporal, which says that if given value is being used right now, it's likely to be used soon. And second, spatial, which says that the things that are located next to each other in memory are likely to be used together. So think of for loops. When we are iterating, we use first element, second, third, fourth, fifth. So CPU does some optimization. When you access the first element of the array and the data is not present in the cache, we have a cache miss. And it copies whole cache line from main memory to the cache because it predicts that you will need the other values very soon. So, usually the size of a single cache line is 64 bytes. And when we try to fit value types and reference types of our example type in single cache line, we can see that we can fit 8 instances of value type and less than 3 instances of a reference type. And it affects performance. I decided to write a benchmark for you. With the help of benchmark.net, we are using hardware counters feature, and we are going to look for cache misses. The benchmark is really simple. We just iterate through an array of value types and reference types, and we just add both fields together. So we are just touching the fields. So it's more like a benchmark of CPU cache. But how do you think, for a big data set, how huge the difference can be? In that case, for 100 millions of elements, doing this with reference types was more than 3 times slower. And as you can see, the cache misses were more than 3 times common. And this affects performance. This is really important to understand modern CPU architecture, because data locality has a great effect on the performance. And other great benefit of value types is that they are not affecting garbage collector. So when you allocate a local variable, which is a value type, it's invisible for garbage collector because it's get allocated on the stack. If you allocate an array of integers, then garbage collector allocates an array on the managed heap, and the integers are inside. They are nested, but it doesn't care for the content. So they are transparent for garbage collector. So anytime you create value type and you don't box it, you don't put any extra pressure on the garbage collector. And you don't allocate any managed memory, which is very important if you want to go really high performance. And of course, for the stack allocated value types, we have deterministic deallocation. When the method ends, the stack is being just unwinded, and everything is being wiped out. But of course, there are some disadvantages. As when you take a look at the basic class library, most of the types are classes. So can you name a few of them? So by default, they are being sent to methods and returned by copy. And it's expensive to copy. If you have a structure that has 5 fields, and you just send it to another method, all 5 of them are going to be copied. When you're doing this with reference types, only value of the pointer is being copied, a single thing. So the copying is also not obvious when it happens. Let's consider this example. We have read-only field which points to value type, and we call just a method on this field. And what C# compiler does, it emits following code for us, because it can see that the field is read-only, so that it should be immutable, but inside of a value type, you can access this keyword, so the method could use this keyword to change its own state. This is why C# compiler is emitting code like this, for us to have the immutability. So there is a way to avoid copying. We should do things by references. And C#7 offers us the way to return references from methods, still accept the references, and create local references. As you can see, the code is quite complicated. And for those of you who believe in clean code and want to maintain the code clean, it's really important that you should use it when you need it. So when you've been profiling your application or designing it for performance, and you are sure that it is required to use references, then you should be using them. You should not use them by default anytime you can. And let's run some other benchmarks. Let's iterate through an array of big structures and just initialize them. Big structure in this example is 5 fields. So when we do it by copy, we take a copy from array, work with local copy, and then we put it back to the array. So we copy it twice. But when we do it with references, we dereference the array item and work with local reference. We don't copy any memory. And the difference is quite huge. In my example, it was more than 4.5 times faster to do it with references, and I have just used ref keyword twice. And as you can see on the chart, we can see old JITs and the new JIT, the reujit and the legacy JITs. And can you tell me how is it possible that this feature works with old JITs? Has Microsoft released a patch for Windows? No. This feature is implemented, this C# language feature is implemented on top of CLR feature called managed pointers. So it's just about exposing an old existing feature that wasn't used before. It was also, of course, about implementing all of the safety rules for the pointers. But some of you can say that we could previously also use pointers in C#, because we could go unsafe, we still can go unsafe. The code isn't pretty at all. We have to switch to unsafe context, we have to pin object in memory, and we have to play with ampersands and stars. So let's compare the unsafe way and the safe way. What I got was that doing it in the safe way was faster, because I didn't need to pin object in memory, and pinning has another overhead for garbage collector because it has an extra work to do. Because in the third phase of garbage collection, it's compacting the memory, so it might be moving objects in memory. And moreover, we didn't need to go unsafe when we're doing this in the safe way. And I didn't know that unsafe have limitations. And a few years ago, I've been running a demo on Azure, and it has failed because the default setting didn't allow me to have a full trust. So if you want to run your code everywhere, you cannot use unsafe because somebody might use it in environment with limited trust, and the code will just fail during the runtime execution. So it can be a no-go. As of today, it's very hard to find some knowledge about the managed references and value tuples. But one of the core members of Roslyn team has recently started blogging, and as of today, in my opinion, this is the best way to learn more about this. So if you would like to learn more about references, you should go to this address, which is quite easy to remember, mustoverride.com, and just learn from the guy that has actually implemented these features. So, to sum up, C#7 performance. Value types have better data locality, and they don't put any pressure on garbage collector. And as you know, no GC is better than any GC. You should use value tuples to have clean code and great performance. And you can use references to get rid of unsafe and to avoid copying of value types. Speaking of unsafe, have any of you ever used stackalog? Okay, one person. So stackalog is a keyword in C# that in unsafe context, it allows to allocate memory on the stack. It's very fast. For small chunks of memory, it's almost 2 times faster than new. So it would be nice to use it. But when we compare all different types of memory, and we have small managed objects, large objects, managed objects, stack allocated memory, and unmanaged memory allocated on the unmanaged part of the heap, we can see that all of them have quite fast allocation, but when it comes to deallocation, there is a huge difference, because the native memory can be deallocated on demand in deterministic way. So you can actually predict how your code is going to behave. When it comes to managed memory, we have garbage collector, which implements a heuristic. So it decides on its own when it's going to clean up the memory. And when it does so, it's suspending all of the active threads of your application. So it's doing nothing else but just cleaning up the memory. But on the other hand, the managed memory is very easy to use. We have enumerable extensions which are known as LinkU. It's common, it's safe. The unsafe memory, have you ever used a public API that was exposing unsafe methods? Yeah, it's really not very common. But now, people at Microsoft, they want to tune .NET. They want to make ASP.NET Core a competitor to other cloud web frameworks. So they need to utilize full power of whatever they can take to be in the top of the tech power. And the other problem that we have when we want to support all types of memory is our APIs. So if you want to just accept an array, it's like this. What if you want to take a part of the array? You accept an array, start index, and the length. Okay, and now let's handle the unmanaged memory. We have 4 methods. And what if we want to specify input and output? So quite many of them, maybe this is why very few public APIs have something like this, and the list is not, of course, full. So the solution is span. Span is a simple type that allows us to work with any type of memory. Stack allocated memory, memory from the unmanaged heap, and memory from the managed heap. It's fully type and memory safe, so you don't need to worry about safety. And it has almost no overhead because it's just about very simple pointer arithmetics. And how do you think? Is it a value type or a reference type? Yes, it's value type. It's stack-only value type. And I will talk more about stack-only soon. So when I said that it supports any kind of memory, we can allocate memory on the stack, create span out of it. Allocate memory with the Marshall API, just use the pointer and create span out of it. We can create it out of an arrays, and we have even implicit cast operator, so you can just assign array to span, and boom, you have span. And as you know, strings are immutable in .NET, so in order to create span out of string, we need to use read-only span, which is immutable. The API is very simple. I would recommend to think of it like of an array which can point to any type of memory, because it has the length indexer, which allows us to get and set elements. It also allows us to do slicing, and this is super important because it takes parts of memory without copying them, because it creates a new span with just a different pointer. It does not copy any memory. This is one of the most important features of span. You can also clear it and fill it, or copy it somewhere. And we have one very nice method with awesome name, dangerous get pinable reference. If you need to pin the span, you should use this method. But I believe that the method might change. The name might change. So previously, when we wanted to support all kinds of memory, with input and output, with all of the variations, we could have something like this. With span, we either have method that accepts one span or two spans, which is input and output. So it simplifies all of the public APIs. And span supports existing runtimes. It's a new shiny thing for .NET Core, but to keep us all happy, Microsoft has decided to support .NET Standard 1.0. So you can actually use span with your old existing desktop .NET applications that target something like .NET 4.5 or something new. But we have two different implementations, one for the existing runtimes and one for the new runtimes. The one for the existing runtimes has 3 fields. So let's say that we want to create a span out of the second half of the array. Then the pointer will point to the beginning of the array. The offset will be the amount of elements to the middle, and length will be just the length of the second half. Why don't we merge pointer and offset? Because the old garbage collectors, existing ones, wouldn't know how to update the pointer when the memory is being moved during the compact phase. So the new runtimes, they have merged it. As of today, only .NET Core 2.0 has native implementation for span. So they've been just merged. It's super simple, 2 fields. And some people call these 2 versions slow and fast span. I have decided to write some more nano benchmarks for you. And in my opinion, the most important part of span is indexer getter and setter. Because what you are going to do with span all of the time, you will be just accessing the indexer, the values. So with benchmark.net, I was able to compare the version for .NET 4.6, for .NET Core 1.01, and for .NET Core 2.0. And as you can see, the difference is not really huge. It's from 12 to 13% slower. So it means that you don't need to exclude span for the existing runtimes in terms of performance, because it's just very fast. And one very important note, there is some place for further improvements. Other assumption and the goal for span was that it's going to be equals in terms of performance with the array. And I have measured it. The red bar is array indexer getter. The orange bar is span indexer getter. So as you can see, they are on par. So this is important, but valid only for .NET Core 2.0, which has the native support for span. For the old runtimes, we would see these numbers again. And as I said previously, the biggest advantage of span is the possibility to create slices without any allocations. So previously in .NET, when you wanted to take only part of given text, a string, you had to use the substring method, which was allocating new memory and copying the part of the string to your memory. And with span, we just do simple pointer arithmetic. When you want to take only the first part of this text, .NET Core, what we do, we create a new span by calling slice, and what slice does, it sets the pointer to the beginning of the string and sets the length to 9. So it's two super simple operations. And when we compare the performance in this very simple scenario, we can see that substring is like 3 times more slower, and it was allocating memory. And one important thing, as you can see, here we are always going to play with pointers and length. So it's size independent because we are not copying anything. So actually the cost of slicing will be like constant in time. The reason why really Microsoft needed span was that they have profiled a lot of web scenarios, web server scenarios, and they have realized that they allocate a lot of memory when it comes to formatting and parsing, compression and decompression. Because what we do with web requests, we parse the web request headers, then we format something, we play with JSONs and stuff. Everything is about strings, encoding, decoding, compression, decompression. As of today, these APIs are not production ready. They are in CoreFX Lab. I would say that they are quite good, but not polished enough. But what I would like to encourage you to is to go to CoreFX Lab, and if you would like to shape the next version of .NET, you can actually do this. So you can actually help others to create the new array, to make it happen. I believe that such chance in the world of .NET wasn't given to us in the last 10 years at least. Span has a serious problem. It's called struct tearing. So every architecture offers us atomic updates, but usually it can update only one thing at a time, and the thing has a size limitation. When you take a look at the interlocked class, you can see that it accepts bytes, integers, shorts, longs, and also pointers, but nothing bigger than that. And in span, as you know, we have at least 2 fields. So it's impossible to update both of them in atomic way. And let's consider this example. We have public class which has a private span field. And we have a public method that allows to update the state, and another public that allows to read the state. And we have 2 threads and state of the memory. When the first thread decides to set the pointer to A and length to 100, first thing it does, it points to A. So the value of memory is A and 0, because 0 is the default value for integers. And then, in another step, another atomic update, it sets the length to 100. Okay, but now we want to set the pointer to set to B and the length to be 1. What we do is another atomic update, and we have new pointer and old length. And the real problem begins when other threads want to read at the same time. Because what it can see is B and 100. And we just wanted to set the max length to 1. So when it tried to read the 10th element of the buffer, it should get array index out of bound exception. But what it got, it read a random value from memory. And how can this problem be solved? Maybe we should synchronize the access. No. Synchronization is slow. If you ever design for performance and you think that you need to synchronize something, I encourage you to do some brainstorming, think about this for a while, and try to find different way of doing things. The solution is to make span a stack-only type. So what does it mean? It means that it can live only on stack. And stacks are not shared between multiple threads. So only single thread can access stack at the same time. No need for synchronization. Moreover, GC has a few pointers to track because the stacks are short-lived. The methods begin and end. Stacks is being unwinded. So at the same time, we will just have few spans on stacks. Moreover, we have safe concurrency and no need for locking. And we have very safe lifetime because when we allocated memory on the stack with stack alloc and we have stack allocated span and the method ends, the stack is being unwinded and everything is being cleared out. The problem is when you have pulled the memory. This is your responsibility as the developer to return it to the pool before the method has ended. But stack only means that we cannot put it on the heap. And this is where real struggle begins. Let's consider this example. We have method that accepts something that implements IEnumerable of t. And we have a value type that implements this interface. And then we just create an instance of this value type and we send it to given method. As I told you at the beginning, value types don't have the method table pointer. So when you want to invoke a virtual method on them, in the non-constrained way, what compiler does, it emits a boxing instruction, which boxes the value and put it on the heap and gives it the method table pointer, and now we can use it as the interface. And the problem here is that when we box things, they are being put on the heap, and heap is not stack. So stack is preventing us from implementing interfaces in that case. This is why span is not implementing any existing interfaces, like IEnumerable, for example. Because somebody could by accident box it and put it on the heap. And it's not the end. When we use async await, it's great for our code productivity, but what C# compiler does, it emits async method builder, which creates async state machine. And at some point of time, it might put all of the parameters that you have sent to the given asynchronous methods on the heap. So this is why we cannot use spans as asynchronous method parameters. Moreover, they also cannot be fields in non-stack only types because they would be allocated on the heap one day. And then they also cannot be generic arguments. A long list of limitations, but only when it comes to passing them as arguments and when it comes to generic arguments. And Microsoft has few ideas how we can make still span usable for everybody. So the idea is not production ready yet. If you take a look at documentation, then they mention something like memory. If you take a look at the code, there is no sign of memory type. It's called buffer now. And it's work in progress. They work very hard. The span is being used in pipelines right now. And really, pipelines are going to shape the API of the span. And the idea to overcome this problem is something to have a type that has no limitations. It can be sent and put anywhere, and it will be our on-demand span factory. So when you want to use span, you just create a span, which will create the span for you in, for example, synchronous context or wherever you need it. And sample implementation could have a pointer to unmanaged heap, and just when you create it, you create a span from the pointer, and when you are done using it, you call dispose, which is freeing the memory. The same comes from for the pooled memory. We can just return it to the pool. But as I said, this API is not production ready yet, and the types are called buffers, and owned buffer and reference counted buffer. If you would like to find out more, you can go to CoreFX Lab in .NET repository and check this out. So let's sum up the span. It allows us to work with any type of memory. It's very fast, it's small, it's just an abstraction for pointer arithmetics. It allows us to create slices without copying memory, which is very important, and it allows us to work with unsafe memory in a very easy way. It also supports .NET Standard 1, so you can use it in your existing applications. It's on par with Array when it comes to performance, but it's limited due to the stack-only requirements, which can be worked around. Now I would like to play a video for you. It's a video from a game. The game is called Age of Ascent. It's being developed by Illyriad Games. The backend is being run on .NET Core on Microsoft Azure. And my question to you is following. What has just happened? Yeah, you were right, GC. Let's take a look at the heap of the managed process. So we have two types of objects, small and large. Anything that is bigger than 85,000 bytes is considered to be large object. Anything smaller is considered to be small objects. And small objects are allocated on the Gen 0. When they survive the first collection, they are being promoted to Gen 1. If they survive another, they are being promoted to Gen 2. And this model works great for short-living objects. If you think of web application, web request starts and ends, and most probably any memory that you have allocated during handling of this web request should be cleaned up. This is why Gen 0 is very small to have very fast collections of small space of memory. But the long-living objects are supposed to live in Gen 2, which is very big, and it's really time-consuming to clean it up. And we have large object heap, which is a separate part, but the real problem is that every large object is marked out of the box as Gen 2 object. So when we run out of memory in a large object heap, GC performs full garbage collection. And this is what we have just seen, full garbage collection in production. What can we do about this? We can just pull the memory. It's a very simple pattern, pull pattern. And finally, we have good implementation that we can use and rely on. ArrayPool is a pool of reusable managed arrays. It has a default max size. It's important. I will talk more about this soon. And it's available in system.buffers package. It's been in production for more than a year. You can use it, don't worry. And usage is very simple. First of all, we need to obtain an instance of a pool. We can do this with shared property, which returns us a shared pool with default max size. If you want something more, ArrayPool has a create method, which allows you to create your custom pool. Once you have it, you rent the buffer, and you specify the minimum length. What you get will be most probably bigger than what you have asked for. You just use it like you used it before when you were allocating arrays with new, and after you are done using it, you just return it to the pool. And yeah, let's take a look at some benchmarks. Let's don't trust the theory. When we compare 100 bytes, we can see that allocating was faster. When we get to 1,000 bytes, it's almost equals. But when we go up and it's 10,000 bytes, we can see that allocating was much slower, like 9 times slower. We don't want to get here. But when we reach the limit of large object, so it means that 85,000 bytes, here we have 100,000 bytes, we get Gen 2 collections, the red color. This is what we want to avoid. So we should be definitely pulling large objects. And as of now, you should observe that the cost of renting and returning is almost constant. It's always, for my box, it's something around 32 nanoseconds. So it's size independent. So you can also predict how long your code is going to take to execute. But when we reach the max size of pool, it has behavior that you maybe wouldn't expect, but when you think of it, it's kind of obvious. When you ask for something that is bigger than the max size of given pool, it's just allocating new array for you every time. And when you want to put it back, it's ignoring the reference to avoid some synchronization in general. So you wanted to save time, but you have actually spent more time and you have allocated the memory. The solution to avoid this problem is that you can create custom pool that is aware of the size. As I said previously, we have the create method, which allows you to create a bigger pool of bigger arrays. Did somebody raise the hand? No. Microsoft wants to help us to avoid this problem, and we have an extra event for that. Events. So we have new ETW event provider, which is called System Buffers ArrayPool Event Source. If you want, you can use Purview to profile and to watch for these events. What you will see is output like this, and what you should be looking for are buffer allocated events. This is the thing that we want to avoid. We want to pull memory. You want to see buffer rented and buffer returned in equal count. So every large object is considered to be Gen 2 object, which means full garbage collection when we run out of space in large object heap. ArrayPool was designed for the best possible performance. It was tuned by people like Jan Kotas and Stephen Tope and Ben Adams. I don't think that we can go any further. It's a pool for pulling managed memory, and you should use shared by default. It's important. Our goal was to keep the large object heap small. When you create too many pools, too many custom pools, you will end up once again with a lot of large objects. So this is something that we want to avoid. And this is why most of the libraries that are commonly used, like Kestrel, ASP.NET Core, ImageSharp, they're using the shared pool, so they don't create any custom pools in your code. And the other problematic scenario that was found when Microsoft was profiling their web application is following. We have a method which is asynchronous. It's executed very, very often. But most of the time, it could be executed in synchronous way. But all of the time when it could be executed in synchronous way, we allocate tasks. And tasks are reference types, so we create an extra overhead for garbage collector. If you want to get some real example, you can think of a network stream. It downloads whole chunks of memory, let's say 4 megabytes. And you might have an asynchronous JSON deserializer working with the stream. So most of the time, stream already has the bytes for the JSON deserializer. So it could provide the data without any allocations. But previously, it was impossible, and it was always allocating new task when the data was already present, was already waiting to be consumed. The solution for this case is to use ValueTask. ValueTask is a discriminated union, which means that we can create ValueTask out of result, something that is a value, is present, or from asynchronous task. So it can wrap non-executed task. And it's supposed to help in this single scenario. Unfortunately, ValueTask doesn't have any other usages. This is why I believe that mostly people who work with networking and creating software for other developers will play with ValueTask. But it's important to understand how can we take full advantage of ValueTask if we are in this scenario. So first of all, we need to check if synchronous execution is possible. If it's possible, we call the synchronous method, and we just return a ValueTask with given result. We didn't allocate anything on the heap. When it's the opposite, we need to call the asynchronous method, which will allocate asynchronous task, and we just wrap it into a ValueTask. And by default, this method is not going to be inlined because it's going to be too big and it's returning a big value type. So you might need to apply aggressive inlining attribute if you also would like to gain benefits from inlining. And how not to consume the value task. We cannot simply await it, because C# compiler will once again emit a lot of code behind for us, and it will make the code complex. And we wanted it to be very simple for our hot path. The solution is quite trivial. We just call the method which returns a task, value task, and it's possible to be inlined. So we have another benefit. And we check for the hot path. Is it completed? OK, I just take the result. Otherwise, I await the inner task. And here comes to play the asynchronous state machine, context switching, and all of this. So we were interested in the hot path, and unfortunately, we have to do it this way, like manually. If we do it in the wrong way, as I showed you on the first example, it's actually going to take more time than when we do it properly. So it's a trap. And as you can see, the benefit is that we don't allocate any managed memory. The difference in time isn't that big. And this benchmark was just about the super positive example for measuring the overhead. So it means that in all of the cases, I knew that I could execute in synchronous, and I was returning simple value. So it's just about measuring the overhead. And as you can see, on the right, we have Gen 0 collections. So for tasks, there were some Gen 0 collections, but there were also some Gen 1 collections. And why did we have Gen 1 collections? So tasks are reference types, and they have finalizers to handle unhandled exceptions. So anytime a GC decides that something is a garbage, but it has a finalizer, it's promoting it to the next garbage collection generation, and it puts it to the finalizer queue. After cleaning up the memory, the finalizers are being executed, and then the Gen 1 can be collected in next cleanup. So they survive at least one generation collection. So it's important to avoid creating a lot of them, if we can, in high-performance scenarios. It's important to remember that it's not about replacing tasks. It's about to help in this single scenario where we can avoid heap limitations, and maybe we can get some benefits of the method inlining. And to do so, we need to play with the isCompleted property and the result property.
Otherwise, is it quite safe in the sense that you won't go into a setup where the task finished just after you check is completed?
Yeah. So the method is implemented in a way that it checks if task is null. If it's null, it checks, it returns true, which means that it was created for a value. And one very important thing, ValueTask is a part of CoreFX, and it's open source. So we can analyze the code on our own. And there is one extra feature for the performance geeks. So as you know, C# is being compiled to IL code, which offers us a lot of features. But C# offers us only a subset of the things that IL can do. Some of them are sometimes required when you want to go really high performance. For example, you would like to do managed pointer arithmetics. Previously, we didn't have managed pointers in C#, so these methods are not exposed in C#. And this class is a simple single IL file compiled for you and which you can consume in your C# code. So if you ever want to get something from IL that is not available in C#, there is this new class which exposes most of the possible methods. For example, if you want to copy memory, it emits the copy bulk instruction, which is supposed to be implemented by runtimes and which is supposed to be the fastest way to copy memory. Another example, if you want to get size of any type, then in C# we have a size of operator, but it works only for primitives, like integers. If you want to get size of your custom structure, it doesn't work. So, but as I said, it's in a situation when you really want to take full advantage of the IL. Who of you have been today to Adam talk about .NET Standard? Okay, and who of you is developing up libraries for other developers? Okay, so we have quite a lot of app developers and also some libraries. So previously, we had, when you were trying to publish a Nugget package, you had to target all of the frameworks that you wanted to support. So if you wanted to support .NET 4, okay, this was your first target. What about Mono? Another target. What about Xamarin? Another target. And here Microsoft wanted to add a few more frameworks. .NET Core 1.1, 2.0, Universal Windows Platform. So what? The people should be now targeting 6 of them? No. And Microsoft has decided to like inverse the dependency. And you can think as of .NET Standard as of a set of interfaces. And now every framework is supposed to implement a standard. And as a library author, you just target the standard. And your code can be executed on any framework that is compliant with the standard. But if you are just a library consumer, then what you need to know is that you need the latest Visual Studio and the latest Nugget client. And then your toolchain will understand what .NET Standard is, and you will be able to use all of the new things in your existing desktop .NET applications. And the good thing is that all of them target almost the lowest standard. Only system buffers, which contains ArrayPool, target 1.1. And as I told you previously, I was supposed to speak about pipelines, but David did, so I decided that I will take this time and speak about something else. And recently I've been watching Microsoft Build. And the PM of C# said something like this during his talk. We sort of want push unsafe code out of C# in a way, or more to the corner, having more low-level code that is safe and efficient. And at this moment, I have smiled. And then he said something like this. You can go to the GitHub and see what is rambling there. So I decided that I will analyze all of the issues, available documentation, language design meetings, notes, and prepare a list for you of all of the new possible features that can help us in terms of performance. But one very important thing, I will now speculate. So I'm not Microsoft employee, I'm not promising you anything, I'm just speculating and I'm just saying about things that I have found. They are in the official repository, but they are plans, they can be changed. First feature, maybe we'll be able to define stack-only user-defined types. So we'll be able to do so by applying the ref keyword in front of type definition. What compiler is going to do, it's going to emit isRef-like attribute. But how can they prevent the old compilers from using this new stack-only types, which needs a lot of safety rules to make sure that everything works correctly? The current idea is to also emit obsolete attribute, which will trick the old compilers. Because when they see the obsolete and isRef-like, they think, okay, this is obsolete. I cannot use it. The new compilers will be able to ignore it. This is the plan. I've seen that a lot of people don't like this idea. And I also have no idea what would happen if I, as a user, would define stack-only type and then decide to make it obsolete. Another thing. So maybe some background information. When I say that CLR offers us type and memory safety, we need to understand how is it done. So when you execute your IL code for the first time, CLR is doing IL verification. So it verifies the IL and it makes sure that you didn't write IL by hand and didn't produce any code that can do some magic with pointers and to create any problems with memory. In that way, it ensures memory safety. When you go unsafe, you have no longer that guarantee. And possible plan is to make stack-only spans, to make it possible to allocate memory with stack alloc and make it in safe context without using the unsafe. The problem is that the compiler will need to implement a lot of safety features and also take responsibility for making it work for all of us in all of the possible scenarios. So this is why I have put 3 question marks here. Another feature, I believe, is that this is one of the rather obvious features. As of today, we can take a reference to a field, but it's impossible for read-only fields. And this is why a lot of people break immutability. For example, if you take a look at the Noda time, some of the value types fields are not read-only, but they should be, just to avoid copying of memory. So we will have a new set of keywords, read-only ref, which for the incoming parameters might be shortened to in. So we will be able to take read-only reference of a read-only field, return a read-only reference, accept read-only reference, but we will not be able to create a read-only local reference. Another thing which was already merged, but to a branch, is read-only structures. So we will have the possibility to define a read-only type. And from now on, as I told you previously, in any method, if you have a value type, you can use this keyword. And you can use it to mutate your own state. So this is why, for now, C# was emitting code like this, to avoid copying, to make sure that you will be really immutable, so nothing bad happens here. So with read-only keyword, the type will be read-only, and this keyword will point to read-only reference. So you will not be able to change anything. So I also believe that it's not only for performance, but also for making immutability a first-class citizen for the C# language, and it might solve a lot of issues that we have so far. This feature is quite trivial. Let's just make the extension methods for value types ref-like. So we don't need to copy when we want to invoke an extension method. And by the way, this is possible as of today in Visual Basic. So Visual Basic, in at least one case, is better than C# as of today. And now bleed-table types. So I told you that we have unmanaged memory and managed memory. And we cannot put reference types to unmanaged heap, because when garbage collector is updating pointers, it would not know that some of the pointers needs to be updated. And we can put some very primitive types on the unmanaged heap, and they are called bleed-table types. So we might have the possibility to have bleed-table user-defined types, and we are going to have compile time verification of all of the safety routines. As of today, the idea, the proposal wasn't merged. There is still ongoing discussion. But what I, as a performance guy, would like to do with this is to extend one of the span methods and to be able to cast spans of one bleed-table types to another bleed-table types. And think of this. You have a network stream which has an array of bytes. You create span out of this, it's span of bytes. But you know that internally it's representing value types, bits, bleed-table value types. So with simple operation like cast, we would be able to get our types without any memory allocations, just with few pointer arithmetics and few math operations, without any allocations. So let's sum up my talk. I would like you to start using value types more often. Please use references to avoid copying and try use them to get rid of unsafe, to be fully safe. You should use span to avoid copying when it comes to slicing. You can use it in parsing, formatting. You can help CoreFX Lab. You can start to contribute and make it happen faster. Moreover, you can also use span to take full advantage of the unsafe memory because it's an abstraction. You don't need to care what kind of memory it is. You should also pull the large objects it's very easy with ArrayPool. You can use a value task, but only in this single scenario, unfortunately. And if you want to go out of C# and use full IEL power, you can use the new unsafe class. And please support C# 7.2 ideas. It's very important. I'm one of the contributors of few repositories, and it's really cool when people click thumbs up, because then the maintainers know that somebody likes this idea and would like it to be implemented. It's very important. It's the first step for our .NET ecosystem. At least say that you like something. At least click once. It doesn't cost anything. I'm not asking you for any donations. So here is the list of all of the sources, which you'll be able to find under this address. I have put all of the places where I took knowledge from. And if you would like to learn more about the benchmarks, here is the link for the benchmarks. So thank you very much.